Welcome. On this video, we will talk about infinite series. So we'll start by taking a look at this small introduction question. Let's consider this infinite sequence. A of n equals -1 to the n. And we're going to start by finding the following sum. We want to find an infinite sum. So what would have happened if we would have added infinitely amount of terms? Are we reaching a value? Are we not reaching a value? Like what happens if I want to add up infinitely many terms? Well, if this is how my sequence is being defined, let's start by just plugging in some values. So let's plug in, so this will be the expression for the first term in the sequence. This will be the expression for the second term in the sequence, third term, fourth term, fifth term. And notice that we want to add up infinitely many terms because we want to go from 1 all the way to infinity. So what exactly do we get here? Well, -1 to the first is -1, -1 to seconds, that's 1, -1 to the third, that's -1, -1 to the fourth, that's +1, -1 to the fifth, that's -1. And we're going to add many of them. But notice what happens when we start doing this. Because notice that here we're adding a lot of terms. So therefore, -1 plus 1, well, they cancel out. This -1 plus 1, they cancel out as well. This -1 should cancel out with the following term, which you might guess that the next term is definitely going to be a +1. So now we stop here and we ask this question. Are all the terms in this infinitely sequence are going to cancel out? And perhaps we can have an expression for our initial sum. Would it be true that, we can see that every single term is going to cancel out with the same one. So would it be okay for us to say that the sum it's equivalent to 0? Because all we're saying is that we got +1 and then the next one is +1 and then the next term is going to be -1. So definitely these are going to cancel out. These are going to cancel out. So if I want to add infinitely many of them, I'm always going to have this pair. So perhaps, and again, every single one of them are going to cancel out. And perhaps you might be tempted to say, yep, every single one is going to cancel. But notice that here, we're going all the way to infinity. So if we take in consideration the same expression, so 1 following by a -1, plus 1, -1, plus 1. So we all, okay, so 2 are going to cancel out, 2 are going to cancel out, 2 are going to cancel out. These are going to cancel out. But since we're going to infinitely many of them, there's always going to be one term after. So notice that now, perhaps, we can see that the sum can be reached to 0. So where exactly are we going? If we keep adding infinitely many terms, are we going to +1? Are we going to 0? Or are we going to neither of them? Well, in conclusion, is that we can say that this is neither. Because it neither goes to 0 or neither goes to 1. Because there's always going to be one more term after the conclusion that you come up with. So if you're saying that the sum is equivalent to 0, I can always find one term after your conclusion and make the conclusion that is -1. And if you're saying that the infinitely sum goes to 1, well, I can always say that the next term is going to be -1 and then go back to 0. So notice that is neither of those two. And this is exactly our lesson for today. So is there ever going to be a situation where if I add infinitely many terms, am I going to be reaching a single value? That's the question that we want to answer today. If I keep adding infinitely many terms, are we reaching a single value? Well, let's take a look at some extra examples. So, and again, this is what we want to say. Well, how can we answer the question, does an infinite series converge or diverge? And again, to converge is to approach a value, and to diverge is to not approach. Approach a value. So if I keep adding infinitely many terms, am I approaching a value or am I not approaching a value? That's the question that we want to answer today. And at least for our first example, let's take in consideration this sequence now, 1 over 2 to the n. And we're going to do this by steps. So the first thing that we want to do is let's compute the first 6 values in the sequence. So let's start by finding the first term, where again, the first term is just 1 over 2, because we let n equals to 1. The second term is going to 1 over 2 to the second, which is 1 to the fourth. And actually, I'm going to leave them all a second. And now the next term, oops, supposed to be a 3, is 1 over 2 to the third. And now the next term, so we want to go all the way to 6. And lastly, it's 1 over 2 to the 6. So here are the first 6 terms in the sequence. So done. Now we want to compute the partial sum. So to compute the partial sum of s of 1, that's just the first term. The partial sum of s of 2, well, that's the first term plus the second term. S of 3 is the first plus the second plus the third. And S of 4, that we're going to add the first 4 terms. And we want to do this all the way to the 5th term. So we got 4 all the way to 5. And lastly, the 6th. And notice that computing all this is going to, it's not going to be a straightforward calculation. So to simplify things, we're just going to jump to decimals. So let's go to decimals here. So here we have our small decimals activity. Notice that f of x is going to represent my sequence now, because right now my sequence has been defined as 1 over 2n. So I'm just going to represent as 1 over 2x. We'll deal with example 2 in a second, so don't even pay attention to this yet. And now notice that here we have our results. So let's plot the terms in the sequence. This will be where my first term is located, which notice 1 over 2, that's 0.5. So we know the first term is 0.5. 1 over 4, 0.25. So notice that this column is going to represent the value of the term in the sequence. So my second term is going to have a value of 0.25, which is exactly what we wanted to get. The third term is going to have a value of 0.125. My fourth value is going to be 0.0625, so which is about here, the fifth and the sixth. Now, if we plot this sequence, what do you notice about this sequence? Well, it seems like the sequence itself, it seems like A of n, it converges to 0. Notice how the terms, like if we keep computing more terms in the sequence, they're all going to be approaching to the value of 0. So we can say that this is an infinite sequence who is converging to 0. So if I have a sequence that is converging to a single value, which in this case it's 0, what would happen if I wanted to define the partial sums? So let's take a look at the value of the partial sums. Well, the partial sums, at least in our decimal illustration here, is going to be represented by the second column. So here notice that all I'm doing, I'm just adding up to certain terms. So the first partial sum is 0.5 because it's literally just adding the first term. For the second partial sum, it's adding the first 2 terms. So 0.5 plus 0.25, that's 0.75. S of 3, I'm adding the first 3 terms. And you can double check this, but 0.5 plus 0.25 plus 0.125, that's equivalent to 0.875. And now, The fourth is 0.93, and the fifth is 0.96. And we can stop here. There's no need for us to compute the six. But now, let's start looking at the behavior of the partial sum. So if I were to compute it, which we already did, we already computed the partial sum. But if I were to plot it, the partial sum in some kind of a function that we do have illustrated here, and if we think of S of n as some kind of a sequence, so if we were to plot it S of 2, S of 3, S of 4, S of 5, S of 6, if we were to plot it this sequence, notice what's going to happen here. We seem to be approaching a value. So if we just concentrate on the partial sum, where this is the first partial sum, second, third, fourth, fifth, sixth, and so forth, notice that the partial sum seems to be approaching the value of 1. So the partial sum sequence seems to be converging to 1. And now we can use this information to answer question F, because question F is asking, is there anything that we can say about the infinite series? So therefore, if I'm adding infinitely many terms, am I approaching a value? And in this case, yes, we do seem to be approaching the value of 1. So therefore, we can say that if I add infinitely many terms in the sequence, we seem to be approaching a value of 1. And this is not a straightforward concept that we cannot just understand right away, because all we're saying is this. If I add infinitely many numbers, I'm just going to get closer and closer to 1. But how come if you're adding infinitely many numbers, you approach a single value? Well, that has to do with how the sequence is being defined. Because notice that we said that the values in the sequence are approaching 0. So there's going to be a point in time that if we're going to be adding all those terms in the sequence, there's going to be a point in time where all you're going to do is just keep adding zeros and zeros. So therefore, we can approach a finite value. So this is one of those examples that situation happens. You're adding infinitely many numbers, but then after a certain point in time, you're just going to be adding zeros. So therefore, the sum of all those infinity numbers are the addition of all those numbers before you start approaching 0, or before your values are getting so close to 0 that we can just assign a value of 0. And this is a concept that is interesting to understand. How come you can add infinity amount of numbers, and you still get a value? Well, if your values are insignificant after a certain point in time, then all you got to do is just add those that came before that insignificantly small number. So that's what we're trying to say here. If you're adding infinitely many terms and you're approaching the value of 1, because that is the convergence of the sequence of the partial sums. But how about if we take a different approach? Now, looking at example 2. Let's take a look at example 2 now. We're going to perform the same analysis. Let's start by defining a sequence. Let's call it A of n. And we're going to do the same analysis. So since this is how my sequence has been defined, let's start by computing the first 6 terms. So my first term in the sequence is going to be 1 to the second plus 1 over 1. My second term in the sequence is going to be 2 to the second plus 1 over 2. The third, 3 to the second plus 1 over 3. The fourth, 4 to the second plus 1 over 4. And let's just compute real quick. So the fifth term is going to be 5 to the second plus 1 over 5. And lastly, the sixth term is going to be 6, oops, to the second, plus 1 over 6. Okay, so fine. These are the expressions for the first 6 terms. And again, we're not going to compute this. Just going to be using a decimal activity. But now notice that I'm changing the equation to g, where g is the equation that I'm defining here, or at least the expression for the sequence. The sequence is being defined as n squared plus 1 over n. So I'm just going to represent it as x. So now that we have it this way, here we can see that the value of my first term is 2. The value of my second term is 2.5. The value of the third term is 333. The fourth term, 425. The fifth term is 5.2. And the sixth term is 6.16. Okay, so now we have defined the first 6 terms in our sequence. Again, we're going to do the same analysis. So the first sum, partial sum, is just the first term. The second partial sum is just adding the first 2. The third partial sum is adding the first 3 terms. And we're just going to do this all the way up to 6. So that's the fourth. That's the fifth, and one more. And again, we're not going to compute this. We're just going to use our decimal activity. So if I would have added the first term, well, that's just equivalent to 2. That's what we got here. The second partial sum, so if I would have added the first and the second terms, that's equivalent to 4.5. If I would have added the first 3 terms, that's 7.83. If I would have added the first 4 terms, that's 12.06. I'm sorry, 0.08. If I would add the first 5 terms, that's 17.2. And if I would add the first 6 terms, that's 23.45. All right, so we have computed that. Now, before we start computing, or before we start looking at the sequence made out of the partial sums, let's take a look at this, the sequence itself. So if we would have plotted the terms in the sequence, notice what type of a sequence it is. We don't know if it's arithmetic, we don't know if it's geometric, or if it's just a regular sequence, but if we take a look at the values of the terms in the sequence, notice that we can say that this is a divergent sequence. Because we don't seem to be approaching a single value. It seems like the points in my function here, they're just increasing in value. So we can just say that this is a divergent sequence. Now, if we have a divergent sequence, notice, how does that affect the sequence made out of the partial sums? So if we consider this sequence, and again, let's just plot that in here. If we just take a look at the sequence made out of the partial sums, notice that this sequence, it seems to be increasing as well. I mean, maybe perhaps not that straightforward on the illustration here. So let's just take a look at the values that we do have here. Notice that the partial sums, or the values of the partial sums, they seem to be increasing without a bound as well, because we're going to keep adding numbers that does not have a bound, and they're increasing in value. So if you keep adding numbers that are increasing in value, so therefore the partial sums are going to be increasing in value as well. So now notice that at least this type of a sequence, it's also a divergent sequence. So we go back to these questions. We already did this. If we arrange our results, notice that we already did it here. This is the arrangement. Let's graph it. We already graph it. We saw that the functions, or at least the value in the partial sums, they seem to be increasing without a bound. And what do we notice about the sequence created in B? Well, it seems to be a divergent sequence. So now let's come back and try to answer the most important question in this exercise, which is there anything that we can say about the infinite series of n squared plus 1 over n? Notice that here we're saying, if I add infinitely many terms that are defined by the sequence, am I approaching a single value? We don't seem to be approaching a single value because we just saw here that if I keep adding infinitely many terms, all those terms are going to be increasing in value. So if I keep adding them up, I'm just going to keep increasing in value. So therefore, we can say that this infinite series diverges. We don't seem to be approaching a value, so therefore it diverges. So if we try to summarize what we just did today, is the following. For any sequence, if the sequence defined by the partial sums, if the sequence defined by the partial sum converges, then we can say that the infinite sequence converges to that value. If we see that the sequence defined by the partial sum, if that sequence diverges, then we can say that the infinite series diverges as well. And then we try to just put it all and make a small summary box. Let's just do that in here. So what we have discussed today regarding infinite series is that an infinite series, well, let's start by defining. So an infinite series is the infinite sum of terms in a sequence. So the infinite series is just, you're just adding infinitely numbers or infinitely terms in this sequence. And now we can say that this infinite series either diverges or converges. So an infinite series converges we can say that the infinite series converges if the sequence of partial sums converges. In other words, if I take a look at S of 1, S of 2, and if I create a sequence made out of partial sums, if this sequence converges, then therefore we can say that the infinite series converges as well. We said that the infinite series diverges well, that is if the sequence of partial sums diverges. If we would have plot S of 1, S of 2, S of 3, S of 4, if I were to plot them and I see that the sequence diverges, then we can say that the infinite series diverges as well. And again, one small example for an infinite series that converges that was given to us under example 1 or the example under activity 1. And an example where our infinite series diverges that was given to us by the example in activity 2. So this is all for today, and this concludes our lesson for infinite series.